Welcome to this video on displacement spectra. In this video we shall be studying how the displacement spectra is to be constructed and why it is required at all. First we take up the design spectrum of different cores. This slide is showing the design spectrum of IS 1893 part 1 2016. So here we have three spectra given, three lines are given for different types of soils: rock, medium soil and soft soil. The basic characteristics of the design spectrum is that it starts at a point in the vertical axis which is 1.0 and then goes straight line, then remains flat for a certain part, then falls parabolically up to 6 seconds given in the code. In the horizontal axis we have the time periods given, and in the vertical axis we have the acceleration ratio, the ratio of the spectral acceleration to the acceleration due to gravity, SA by G. So how we use it? We take up the time period of any structure either through dynamic analysis or the approximate formula given in the code, and from the time period we go to the corresponding type of soil, the corresponding curve, and come horizontally left and get the SA by G ratio. From that you can get the base shear. Similar is the case with the design spectrum given in ASCE ACI 716. The pattern is same. The other parameters are given here which are explained in that document. This is for the European code EC8 2009, a very similar type of diagram, rising, flat and falling parabola. The equations of all these will be given as in Indian code. In all the codes, the equations of all the lines are given. So if you want to mathematically convert from one to another, from design spectrum to displacement spectrum, those mathematical formula can be directly used. So design spectrum give force demand. Force demand means the amount of force that your structure is expected to experience, and the design force is obtained from that force demand only. So let us take the base shear formula for Indian code. BB equal to Z by 2 I by R SA by G into W. Z is zone factor, I is impedance factor, R is response reduction factor, and SA by G is spectral acceleration ratio. W is seismic weight. We rearrange this formula this way: W by G we take together, and this is a constant part, then SA, and W by G, weight by G is equal to mass. So we can write this expression as M into SA. M is mass of the system. Now mass into acceleration, spectral acceleration is also acceleration, is nothing but force. So we can write dV equal to a constant into force. So your codal formula will finally give you a force, and this is the design force. So force remains in the core of the design procedure in codal procedures. That's why the process, the design procedure, is also known as force-based design, FBD. But why do we require a displacement spectra? Because we may not always design for a force, but we may like to design for a displacement or a displacement demand in more particular. So if we can estimate the displacement demand for a system, then how to design the system finally, what is the associated force that we want to get from the displacement spectra. So when design is based on the displacement demand, displacement spectra will be required. In force-based design, we find the force demand corresponding to the elastic time period of the structure, as we have discussed. In the horizontal axis of the codal demand diagram, design spectrum, time period is given. Corresponding to the time period, we find the spectral acceleration, and the spectral acceleration will lead you to the amount of base shear. In contrast, in performance-based design or displacement-based design, we find the inelastic time period. What is this? We shall see in the next slides. From the known displacement demand. So here displacement demand is known to you. we have estimated it through some engineering process, and from here, from this displacement spectra, we shall find out the inelastic time period associated with the system and then proceed for the design. So how do we construct it? Construction is easy. We simply follow the relationship SA equal to omega square SD. SA equal to spectral acceleration. Omega is the angular frequency of the system, and SD is the displacement demand, spectral displacement. So we know omega equal to twice pi by t. So if we substitute equation 2 in equation 1 and get the value of SD, then SD comes out like this in equation 3. SD equal to t square divided by 4 pi square into SA. So in conversion, you can take one point, you look at the equation 3, one point where you know the time period t and corresponding SA, then putting in this formula 3, you can get the value of SD. So we have taken a design spectrum here, schematic design spectrum, and we have taken one point here. The point is designated by T1 SA1. So corresponding spectral displacement SD1 is given by T1 square by 4 pi square into SA1 as per equation 3. Now in the displacement spectra, your horizontal axis will be time period and particle axis will be spectral displacement SD, in contrast to the spectral acceleration in normal design spectrum of the code. So corresponding to this point that we have shown in the codal design diagram, we have converted to the SD1. So we get a point in this displacement spectra which is T1 SD1. So this formula can be taken for another time period T2, T3, T4 and so on, and corresponding spectral displacement obtained this way from equation 3, and you can get a series of points and join them, and that will be your displacement spectrum. So let us see the 5% damped elastic design spectrum of IS 1893-2016. Why 5%? Because 5% damped system is damping is taken inherent in the all codal design spectrum. Typically 5% is the damping arising out of concrete structures. So at this damping, which is the material damping arising out of the material, the structure has not got damaged till now. So the 5% damping indicates it is elastic structure without any damage. So the corresponding displacement diagram or displacement spectrum for IS 1893-2016 at 5% damped condition is this one. So you have to put the associated zone factor. If you take for medium soil, you get one curve. If you got soft or hard rock, you get another curve. And typically afterwards, you have to apply the zone factor that we shall study in our new videos to come for performance-based design. Now, in the previous slide, we have shown the displacement spectra for only one damping and 5% damped elastic spectrum. But if we wanted other damping, then it will look like this: 5%, 10%, up to 30%. As you increase the damping in the system, the response reduces. So the displacement spectra are coming lower and lower gradually. Same thing if we see in the EC8 code for soil type B at various dampings, it is like this. We have shown here from 5% to 35%. This curves you can get by through Excel sheet. If you put the formula given in the code and take various time periods, then you get this. And the conversion that we have discussed from the design spectrum, you can get the displacement spectra like this. At the start, for some time it is non-linear, parabolic, then straight line, and at a particular time period, depending on the codal prescription given, it becomes flat. The flat part indicates it is not sensitive to spectral displacement based on time periods. We have to also mention that in EC8, the zone factor is not there, and there is no peak value of any seismic level. So it is depending on the user's choice that he can choose what level of seismicity to be considered. For this diagram, we have considered 0.45 G level. If you take some other level, then these lines will be changing their position. Now, how to plot the displacement spectra for any damping? We have shown those in our previous slides, but how to get those for other than 5% damping we have not discussed. Let us see it here. For converting the spectral acceleration of 5% damping, which is given in the code, to any other damping xi percentage, you can use this formula 10 divided by 5 plus xi percentage. Suppose the damping is xi is 5%. In that case, 10 by 5 plus 5, it becomes 1. That means it remains this 5% damped spectrum. If you put another value of xi, then you get corresponding spectral acceleration corresponding to that damping. The similar formula you can also use for spectral displacement. SD xi percentage equal to 10 divided by 5 plus xi percent into SD 5%. SD 5% you have already obtained through the conversion process we have shown in the previous slide. And multiplying with this factor, you can get the spectral displacement for any other damping and plot it. That way, we get the series of displacement spectra for different damping for any design code corresponding to the design spectrum. Now, there is a terminology, effective stiffness and effective time period, that we can clarify here. We start with the simple time period formula for a vibrating system. T equal to twice pi under root m by k. M is mass, k is stiffness, and T is the time period for the vibrating system. So rearranging this equation 1, we can put the value of k this way, 4 pi square by T square into m. This is equation 2. Now we introduce a new term here, the effective stiffness. So effective stiffness also will follow equation 2. So we simply substitute k by k effective and m by m effective. So equation 3 gives the effective time period based on the effective mass of the system. Let us take a force displacement diagram for a structure. Displacement on the horizontal axis and force on the vertical axis. Then red line is the force displacement response. Initially it is straight line. Then some damage takes place, it becomes nonlinear, and gradually more and more damage, more and more nonlinear, and finally it snaps out here. If you draw the tangent at the initial line, then this is the initial tangent. Slope of that tangent will give you the initial stiffness k. So k is the initial stiffness or elastic stiffness of the system or the undamaged stiffness of the system. Now the system has got damaged in all these localities, more and more damages as we proceed towards right. We have taken arbitrarily one point here where some damage has taken place. The damage can be quantified by the amount of plastic rotation that it has undergone from here to here. Initially rotation will be elastic, then when damage takes place rotation will be plastic, and up to here whatever plastic deformation, that is the damage state of the system. If we join this with the origin and this point, then we get a line, and the slope of this line is called the second stiffness or effective stiffness. So this is the concept of the effective stiffness given by equation 3. If you take point at any other level here, here or here, you will get different values of effective stiffness based on the damage state. So this is the physical meaning of the effective stiffness. Now what is effective mass and effective time period? Effective mass is the mass of a system when the multiple degree of freedom system has been converted to an equivalent single degree of freedom system, so that all the masses are represented by an equivalent mass. The system to have the same overturning moment as it was in the multiple degree of freedom system as in the equivalent single degree of freedom system. So that mass is the equivalent mass ME. Effective time period is given from equation 1 again. putting the effective mass and effective stiffness here in the equation 1. So T equal to twice pi under root me by Ke is the effective time period. Effective stiffness is a physical quantity, as you can see here from the force displacement response. In contrast, effective time period is a concept and given by equation 4. Now, how to get the effective time period from this design displacement? So, design displacement means the spectral displacement is given to you. Let us consider EC8 soil EC8 spectrum at 0.45 G level, as we have seen in the previous slide. So, in this spectrum, suppose you have already calculated for your system the spectral displacement point 0.55 meter and the damping in the system, effective damping is 10%. You have calculated this using some engineering principle, some dynamics, some procedure. So for this, we want to find the effective time period for the system. So at spectral displacement 0.55, you draw a horizontal line. And this line should touch up to your damping, which is 10% damping here. So this red line. From this point where it has met the damping line, you draw a vertical line. This vertical line is touching at the time axis, and the corresponding time is your effective time for the system. So T equal to here 3 seconds. This is the effective time period for the system. So this is a virtual time period for the damaged system. Thank you very much for watching. Please subscribe the video, like and share it, and you can put your queries in the comment box. I shall be glad to answer those. Thank you.